talk a little bit about some of the theoretical behind NoSQL. We're going to talk a little bit about several different NoSQL variations and whatnot. I'm not going to go any too deep on any one of them. So if you're here basically to learn everything you need to know about CouchDB in order to put it into production tomorrow, you're going to be sadly disappointed. Okay? I'm not here to teach you everything you need to know about a particular NoSQL variant. I'm here to show you some of the more popular ones and then turn you loose to go discover more. Okay? Loosely speaking, this is a talk designed to make you dangerous. You will know enough about it to convince your manager, but you will not be able to actually do anything credible with it. Okay? So I feel a certain, responsibility towards. Don't go out and build, don't build a mission critical something on this based solely off of this talk. That's me. If anybody cares, most people don't, so we'll move on. Like I said, the goal here is to kind of go over NoSQL. The goal is to sort of describe many of them, go over some of the conceptuals, et cetera, et cetera. There's only so much that we can do in 15 minutes, so don't expect too much. That's all I'm going to say. And to start with, I'm not particularly fond of the term NoSQL. I mean, essentially, as a descriptive term, it's crap. Because on the one hand, we have SQL, and on the other hand, we have NoSQL, which I guess is like everything that's not SQL. So technically, the color purple is NoSQL. Ferrari is NoSQL. The O'Reilly bag in his hand is NoSQL. It's a useless term, right? Now, the NoSQL term sort of began as kind of a rejection, if you will, of things relational. And to a certain degree, that is not an unfair position to hold. As a matter of fact, I have a buddy of mine, Neil Ford, who's spoken at this conference for many years prior to this and so forth. And Neil has, basically, he believes, he has a theory that we will look back at the 1990s and the 2000s as essentially the dark ages of relational dominance. That in fact the status to which we have given the relational database as the only place we would ever store stuff will be looked back upon and realized that was actually probably not a great idea. Okay? That in fact the relational database is a useful creature, don't get me wrong, but in fact the default status it assumes right now as the only place you would ever be willing to store data is in fact a bad scenario. How many of you have wrestled, for example, with trying to figure out how to represent a hierarchy in a relational database? Why? Why? The hierarchy is not something that a relational table-based model would ever represent well. Why would you do that to yourself? How many of you have ever wrestled with trying to store an object graph into a relational database? Now come on, all you got to put your hands up because you all write in Java. If you've never used JPA or Hibernate or written your own object relational mapper, then clearly you wandered into the wrong conference. Because this is a Java show, and Java is an object-oriented language, and we struggle on a regular basis, on a routine basis, with how do we take our nicely, richly defined domain models and store them into a relational database. And I have to ask why. Well, largely because the relational database has assumed this level of prominence, A, because it's what all the enterprise operations folks know, but beyond that, the relational database has reached this level of prominence largely because, A, we have a whole slew of generic tools that know how to interact with the relational database. We have reporting tools that know how to reach into your schema and pull data out and present it to people in nicely, brightly colored formats with, graphs and pie charts and all that other good stuff. We have easy tools to get at that data and do stuff with it.
The other thing, though, quite frankly, is because of that generic uniform interface, that interface, of course, being SQL, because of that generic uniform interface, we frequently use the relational database as a point of integration.
How many of you have ever been a part of a project where you were not allowed to change the database schema at all? Because if you did, you would break 27 different data feeds that take data inserted into this database and go shove it someplace else. This is what I mean about the relational database being a point of integration. And for a lot of people in the enterprise, the classic Java-based enterprise, the idea of getting away from that isn't just about this project, it's about everything else that surrounds it. And these are not problems that the quote-unquote NoSQL databases try to address. They're not going to try to take away from the relational database the things that the relational database does well. So at no point during this discussion do I ever want to give you the impression that I am suggesting that you should go off and remove all of your relational databases and replace them with a NoSQL variant, because quite frankly, you will be doing yourself some irreparable harm. We won't even talk about what it'll do to your career. All right? And if you come back and blame me for it, I will so kick your ass. Okay? These are nothing more than tools. At some point, the folks who are responsible for NoSQL, the term, came back and tried to offer a bit of revisionist history that said, well, you know, NoSQL is actually an acronym that stands for not only SQL. Bullshit. You meant exactly what you said when you said NoSQL. You were rejecting the relational database, and for certain problems, that's exactly the right thing to do. Okay? And so what we're going to do as part of this discussion is we want to sort of dig into this crop of databases, because now it seems like we're finally approaching a point where we can accept the idea of a polyglot persistence world, a polypersist world, that says, you know what, let's use the right storage technology for the problem at hand. Last time I checked, there's not a construction worker in the world who walks onto the job site bearing just a hammer. No matter how good a hammer it is, it will not screw screws very well. Let's use the tools, right? As a matter of fact, as you can tell, I'm from the United States, in case that wasn't obvious to everybody already. And, you know, when visiting socialist Europe, because that's how we look at you guys. You're all looking just a bunch of socialists, right? The words of Karl Marx come to mind. To each project, according to its need, from each database, according to its abilities, to each project, according to its needs. I'm pretty sure that's what Marx said, right? It's just he got lost in translation. So, and of course the Russians went off and they did all kinds of crazy things with their form of persistence. But we'll talk about that later. All right. The theory behind these alternative storage systems, one of the things that's happened over the last couple of years is we've got a few more people using the internet than we used to. Don't know if you noticed this, but compared to where the internet was back in like 1995, there's a lot of people who are on this interconnected web of networks, which means there's a lot of people who are using the various services that you offer, that your company offers, that you would like to offer, etc. We're approaching a point where those numbers are making a difference in terms of how we design things. Werner Vogels, who is the CTO at Amazon, which I think we can agree knows a little something about scale, maybe. Each node in a system should be able to make decisions purely based on local state. If you have to do something under high load with failures occurring and you need to reach agreement, you've lost. In other words, when we start talking about the transactional model, the two-phase commit model that we've all sort of learned and absorbed in through the skin as a part of sitting through all these JEE talks, transactions, et cetera, et cetera. If I have to start doing this two-phase commit model with more than 2 or 3 nodes at a time, and remember, it's a two-phase thing, so we have to have one set of round trips to everybody to gather that, make sure everybody votes yes, and then another set of round trips to in fact pass that on to everybody else to indicate that this transaction does in fact complete. And oh, by the way, while we're doing all of this, nobody else gets to touch any of the data that are locked as a part of this transaction. All of a sudden, when we start talking about trying to do large-scale transactions, when we start talking about trying to do not just thousands, but hundreds of thousands, millions, billions simultaneously, anytime we have to create locks, we reduce the scalability of the system. And as a result, there's going to be an inherent ceiling on the scale that we can achieve. This led in 2000 to a gentleman by the name of, I believe it's Justin Brewer, to create what he called the CAP theorem, which says essentially consistency, availability, partitioning, pick 2. You get to pick 2. It's kind of like what we say in software, right? Better, faster, cheaper, pick 2. It's the same story here. When we're talking about a database, you can either have it consistent, you can either have it available, or you can have it partitioned, but you can't have all 3. We've tried. The relational database has for years held that consistency and availability are king. As a matter of fact, we hold this notion of consistency so ridiculously high that the idea of data being out of sync somehow feels like a sin. Like you're going to go to hell if data is in fact inconsistent for any length of time. We use, quite possibly, the only example that would really strike near and dear to an American's heart. We use money as the example, right? We say, hey, if I want to transfer $100 between myself and, what's your name, sir?
Alex.
Alex, right? So, I don't know, Alex is going to give me $100 because he likes me. Whatever. We're gonna create a transaction. We're gonna debit his account $100. We're gonna credit my account $100, and all of the asset properties kick in here, right? Atomic, consistent, idempotent, durable, etc. And if either one of these, for whatever reason, fails, then, you know, like for example, I have too much money in my account, so therefore I can't take the 100. I don't know how that's supposed to work, but you get my point. If either one of the parties, I don't think he looks poor, so it wouldn't be that he doesn't have enough money in his account, right? For whatever reason, if this transaction cannot be completed, bam, immediately the deal is off and everybody goes back to the state that they were, right? That's the beautiful thing about transactions. If the transaction can't complete, it's as if it never happened. It's like changing history. Personally, I want to live a transactional lifestyle. You go out to the bar, you have too much to drink, you wake up in the morning, oh my God, roll back, and it's like it never happened. You go out to the bar, you have too much to drink, you wake up in the morning, look over, oh shit, she's ugly, roll back. You forget your anniversary, roll back. I want to live the transactional lifestyle, right? But the funny thing about the financial example is that that's not the way it works in the real world. Have you ever tried, I don't know if this is true of European banks, I'm willing to bet that it is, but if you walk into an American bank with a large enough check, right, you walk in with like a $10,000 check, your aunt just died, and this is your inheritance, and you say, I want to deposit this check, the bank will actually put a hold on the money. They'll say that you have it in your account, but you can't touch it yet. It's like, why? Are you just teasing me? You don't fuck with me enough, so now you have to take the money away from me, but not let me add it? What they're waiting for, of course, is to make sure that the fund's clear on the other side, right? But I thought that when you wrote the check, that money was immediately debited from the account. I mean, this whole atomic transaction model, that's how it's supposed to work, right? But it doesn't. If you look at what the banks do, as a matter of fact, in terms of ATMs and whatnot, when they give you 100 euros in cash, they actually keep a ledger of all the ATM disbursements they've made. And then they settle up with the other banks later offline in an asynchronous fashion. They are eventually consistent. This is why, for example, when you're balancing your checkbook, you've written a check, but the check hasn't been cashed yet. You have to remember that that check is still out there to make sure that the $150 or whatever for you know that cool iPod you just bought, you need to make sure that money's still there, because when the check finally comes around to clear, you need to make sure there's money there to clear it. Because banks are not transactionally consistent, they're eventually consistent. As a matter of fact, there are a lot of people in university who have figured this out, and they write checks to one credit card, and then write another check to a different credit card, but post-date it by a couple of days. And so they do this sort of revolving thing. And then you wonder why the US is in such a financial mess. But be that as it may, that float period, you can actually do all kinds of fun things in that float period. You can make like $100 look like it's $1,000. Just by writing the same check, $100 all the way around, and then doing withdrawals from credit cards. And technically it's fraud, but, you know, I mean, if like, you know, if the big banks can get away with it, why can't I? This is what we mean about consistency and about relaxing some of that stuff. When we talk about consistency and availability, the relational database held that as the paragon goal, as the principal concern of data, is to make sure that it was always up to the second, up to the microsecond consistent. Now, it turns out that there are a lot of scenarios. Like I said, the financial industry is actually not transactionally consistent. It's eventually consistent. There are other scenarios that this model works fairly well for as well. For example, how many of you have bought something off of Amazon? Yeah, come on, everybody's hand goes up. You're all geeks. You're all at a geek conference. I know you have. When you go up to the Amazon book catalog, I tell you that I've published a book. When you go up to the Amazon book catalog and you don't see the book there, who do you think is wrong? Right? I mean, seriously, if I told you that it's done, it's the manuscript's been handed off to the publisher, etc., and you don't see it in the Amazon catalog, does that mean that Amazon is incorrect? As it turns out, it's entirely possible that Amazon does have all the details of my book. They're in their database, but they haven't rolled it out to all the edge servers yet. Do you care? Generally speaking, no, because you don't even know. When you go to Amazon and you order a book and it says only 3 copies left, and 7 of you order the book simultaneously, what happens? 4 of you get a message from Amazon saying, "We're sorry, it turns out we don't have a book in stock, which means your order detail will now be 2 weeks instead of 3 days. If you want to cancel your order, you may, blah, 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 otherwise click here to continue." Amazon, both in terms of their book catalog, the products that they make available to you, and in terms of the inventory that they offer you, are eventually consistent. Why? Because it's too bloody hard to try to make it transactionally consistent, and it wouldn't make a difference even if it were transactionally consistent. It would actually create more problems. When you fly on an airplane and somebody on the, they always sell, like if there's 140 seats on the airplane, they sell 150 tickets. Why? Because 10 people never show up. Who are those 10 people? I mean, seriously, you're going to pay money for an airline ticket and then not show? I want that kind of money. But they figured that out, that 90% of the time they can oversell the aircraft and still people won't show up and be able to fly. This is what we mean about having some degree of forgiveness in our consistency model, right? Most of the time the relational database goes for consistency and availability, and they surrender the partitioning capabilities. The NoSQL, quote unquote, collection of databases, most of them, I shouldn't even say most, a fair number of them prefer to go for the availability and partitioning. Because partitioning means that we don't have to rely on one giant server to hold all the data, which of course, by the way, creates a single point of failure. We're all very, very well accustomed to that. Partitioning means we can spread it around in a ring, we can have lots of nodes, we can have a certain amount of backup fault tolerance, we can also get larger amounts of data, et cetera, et cetera, et cetera. And when we start talking about amounts of data, you know, a lot of times people are like, come on, you know, my relational database can hold like, you know, I don't know, 10, 20 terabytes, we're doing just fine. There was the Seattle startup scene. I live in Seattle. Actually, I live in Redmond, Washington. I do have very good friends who work for Microsoft. You know, it is possible to be friends with Microsoft and not have to buy their stuff. I'm just here to tell you that. Seattle has a very thriving startup scene, and we were having there's actually a group of startup entrepreneurs and so forth who sort of formed into a technology, basically a user group. And we were having a meeting on NoSQL stuff, and one of the guys who was presenting was talking about how his startup was using Cassandra. And somebody asked, well, I mean, what amounts of data are you really storing when it comes to Cassandra? You say you're storing a lot of data, but really, what does that mean? And he said, on a given daily basis, this is a startup, if I remember right, that deals with auto parts. Literally, they want to track every single auto part ever made throughout the history of mankind, right? Even that 57 Studebaker, right? They want to track all those parts because there are people in the world who care about that stuff, not me. And he said, on a daily basis, we work with about 50 petabytes of data. Now, here's an interesting intellectual exercise. On Monday, when you go back to the office, walk up to your Oracle DBA and tell him that the next project that the company wants you to work on is estimating that they're going to need to store 50 petabytes worth of data, and would he mind working out exactly how we're going to do that using the Oracle data? When you do this, by the way, make sure that the doors are locked. Because if you are not careful, he'll think you're serious, and he will immediately run for the door, and he won't even stop to print his resume. He'll be doing the entry on DICE as he's leaving. Because that's just, I have yet to meet any Oracle DBA who's willing to take on that challenge. 50 petabytes worth of data, and oh, by the way, it has to be all accessible all the time. Not going to happen. Because the Oracle database is not set up for that kind of scale size of data. And of course, then we start talking about where Google is in terms of their map reduce and scaling, capturing the entire web, et cetera, et cetera. When we start talking about petabytes, exabytes, zettabytes worth of data, which is not unrealistic in the coming decades, the relational database is a useful tool, but it was never designed to hold that kind of data, that scope of data. It's also not designed to read and write that data quickly. Same guy was talking about how they, as an experiment, they took 1/1000th of the data, 1/1000th of those 50 petabytes, and they tried to write it to a MySQL database with all of the transaction stuff turned off. In other words, they tried to optimize the hell out of MySQL, and it still took about 1,000 times longer. There's a price that we pay for the consistency guarantees that a relational database gives us. And sometimes it's an acceptable price and sometimes it's not. And when it's not, it's nice to know that there are other tools available. So, within the quote-unquote NoSQL world, one of the things we discover is that once we sort of step back from the relational model as the only way of storing data, turns out there are a lot of different ways to store data. Some of these are actually very, very old ways of storing data. Some of these were in fact first done by flat files and ISAM databases and so on and so forth back in the 50s and 60s and 70s. And when the relational database emerged on the scene, the popularity of SQL, the ability to let users write their own SQL queries. Did you know that? That was actually one of the reasons why relational databases were so popular. We could drop the ISQL prompt. We could give them the SQL terminal, our end users, and let them write their own queries against the database. Talk about user friendliness, right? Just Write your own damn query. Why are you bothering me? Write your own report. Get out of my face, right? That was literally one of the selling points of the relational database. Clearly, we're not there now. And once we step back away from that model, we realize there's a lot of different ways to store data. We can certainly, I mean, back in the 90s, the object database was particularly popular in the sense that it was sort of deemed hip. And one of the things that happened there was object databases couldn't, at the time, perform to the same level that the relational databases at the time could. The object databases actually have gotten a lot better in recent years, but by this point they've developed a reputation that say they're slow, they're inconsistent, they can't do transactions, they don't store data, fast enough, et cetera, et cetera. And the rise of the NoSQL concept has sort of given new life to them in some respects. But on top of that, we have some that are just basic key value systems, right? These are name value pairs, the end. There's really no other larger grouping beyond that. The so-called big table systems are often key value systems. There's document-oriented storage, where in fact, at the end of the day, if we drill down through all of these far enough, you'll get to a point where it's just key values. So it's not just identifying key values, but it's also saying, hey, there's a larger grouping here as well. There's the way in which these key values are associated, etc. For example, they may be collected under a document, right? A document literally in the sense of like a blog post or some other more or less star kind of data, where I've got a single grouping here which has some ancillary data associated with it, but heart and soul, it's this thing here. The blog post may have some comments associated with it, may have some attachments associated with it, may have some metadata in terms of when the post was written and who wrote it. But at the end of the day, the heart and soul of this model is the blog post. That's more or less a document-oriented style of data. There are graph databases. Facebook, right? The whole notion of not just who you are, but who you know, and how you know them, and how long have you known them, and what is your current level of relationship, and so forth. Trying to represent that sort of a graph in a relational database is just ridiculously hard. If we've got a database that models nodes and arcs directly and allows us to hang data off the arcs as well as the nodes, we can much better model this. And so, for example, if you want to try to capture the traveling salesman problem, in terms of representing the cities and the distances between them, that's intrinsically graph data. So let's just model it that way, as opposed to having a large table with every city and the distance to every other city, which is obviously an n squared kind of thing. We have column-oriented data, where we have columns and we have some concept of tables sometime, but there's no notion of relations or rel vars like we have from the relational world. We have hierarchical databases, where the data must fall into a strict hierarchy. A lot of times, this is where the hierarchical storage became XML databases back in the early 2000s. Remember when XML was, oh yes, this is the data format of the internet. I remember reading that several times, so it must have been true. And there was a lot of discussion as to how XML databases were intrinsically, naturally a nice synergistic fit with object-oriented languages. They said the same thing about relational databases back in the mid-90s as well, by the way. And they're saying the same thing about document-oriented databases and some of these other NoSQL databases as well. At the end of the day, the only thing that really nicely stores objects naturally is an object database. Other than that, you're going to have some level of impedance mismatch trying to fit an object from an object language into something that's not object data. So the graph database, right? We have nodes, we have nodes. Ooh, objects, we have objects and objects. But here, this object holds a relationship to this other object. There's no way to decorate. There's no way to hang any data off of that relationship. That would have to be represented by yet another object. There's going to be an impedance mismatch for any of these when going against an object language. Just accept it. Okay? You will read, for example, how MongoDB is absolutely perfect for object databases. that's crap. The document-oriented nature, where I have a single object that sits at the start, the center of my object model, yes, we can certainly see object models that are sort of document-oriented. They have that same shape. But as soon as we talk about two-person objects, each of which holds a reference to the other through the spouse field, trying to represent this in a document-oriented database is no easier than representing it in a relational database or a hierarchical database. Okay? You have to do certain kinds of encodings and mappings and so forth. Excuse me. And there are some distributed peer stores where we're basically saying, we're just going to take data in a fairly raw form, but we're going to scatter it all across a collection of nodes with a certain amount of replication, and you just treat the entire thing as one giant file system. There's a lot of different shapes to this data. And one of the things I'm going to suggest, one of the things we're starting to realize is that the various things that we work with often fit one or more of these shapes better than just the relational model. So for example, if we're talking about your bank account logically has nothing to do with any of the other accounts that sit next to it in the table. As a matter of fact, your one account, your savings account, really has nothing to do with your checking account. Rarely does the interest earned on your savings account matter based on the amount of money in your checking account or vice versa. They're more or less independent data elements that happen to be linked together through you. So perhaps this is better modeled as, for example, a document store, where we can say, look, you have a database, or you have an account, and that is the document, quote unquote, and it has a balance, and it has people who are associated with it, et cetera, et cetera. But for the most part, we don't care who the customer is when we're calculating interest. We just care what's the account balance and can we update it, and we have literally millions, if not billions, of these accounts that need to all be processed simultaneously as quickly as possible, et cetera, insert discussion about MapReduce here, and so on. Okay? Think the problem through, don't assume it's going to go to a relational database. All right. So talking about some of these in specifics. First of all, the list that I sort of chose arbitrarily, well, not entirely arbitrarily, these are the ones with which I'm more familiar, just to be 100% honest about it. So I'm better suited at answering questions. I've used the first three. I've looked into the last two, Cassandra and Neo. This is not to say that they are better than any of the other ones out there. They are sexier. These are the ones that sort of, if you say you're going to do a talk on NoSQL and you're going to talk about Couch and Cassandra and so, you get a lot of people in the room. Apparently it's worked. So, but again, I don't want to imply that these are better than any of the other ones out there. And there are literally, I think at last count, there are like 4 dozen different data stores that want to classify themselves as NoSQL, because it's hip. Berkeley DB has classified itself as NoSQL, right? That old ancient Unix-based, we want to just shove something into something that kind of has tables inside of a data file. SQLite. I heard somebody explain the other day to me that SQLite is a NoSQL database because you don't access it over the network. Okay. I'm not sure if you understand what the word NoSQL means. That word no, I do not think it means what you think it means, if you'll pardon my Princess Bride. All right, so we'll start with DB4O. Again, this is an object-oriented database. One of the most interesting things about it is that the query language for DB4O is the programming language. DB4O supports both Java and .NET. You write your queries in Java, or you write your queries in C# or VB if you're using the .NET variation. It's what they call native queries. The DB4O system will actually do bytecode analysis on the compiled code. When you pass a predicate instance in as the query, they look at the compiled method and realize, okay, you're accessing this field and you're doing a greater than or equal to the constant 21, therefore we now know how to query the database. So you don't have to learn a new language in order to use DB4O. You don't have to go off and try to pick up a new object query language. That was one of the drawbacks to the object databases of yesteryear, of the previous decade. They tried to define their own query language, OQL, which ended up looking a lot like SQL, but not in a good way, in kind of a bad way. Because what it did is it left everybody going, why would I want to use this instead of SQL, which has all these additional features that this doesn't have, et cetera, never mind. Okay? It's strongly typed. It's strongly typed to the object types. So when you sit down to work with DB4O, your schema is your Java class. As a matter of fact, you don't even need any annotations. They don't even have any annotations to describe how this thing should persist. The class is the schema. And if you refactor the class, DB4O, like if you add a field, DB4O will silently refactor the data format, the actual schema in the stored data file to keep up with the change in code. So refactoring, if you're working with a rich domain model and you do aggressive refactorings, one of the hard parts has always been to try to keep the relational database up to speed, not only altering the table, but copying all the data over from one table to the next. If you look at the Refactoring Databases book by Ambler and whoever else, I can't remember the other guy who wrote it, Thoughtworker, basically that book is like 57 ways to use stored procedures in views. I mean, it's literally, well, when you're refactoring the table this way, create a new table, but create a view, and then use a stored procedure with triggers. Really? You want to go through all of this work? I don't. I want to use something that sort of lines up with this. And this is one of the reasons I like it. I mean, I'll admit it. I like DB4O, particularly in those cases where persistence is entirely an implementation detail. Okay? If you're storing data, for example, behind a service boundary, who cares how you're storing it? This is true for any of the non-relational forms of storage. I don't really care how you're storing it. Use whatever makes sense. If I'm writing in an object language, particularly if it's in the early days of a project where we are constantly refactoring, this makes so much sense. Productivity goes way high. You want to store 50 petabytes worth of data into DB4O, it will collapse. It does not have the scale. This is a case where this is a database that goes for consistency and availability. It does not have the partitioning capabilities, but it qualifies as a NoSQL because there is clearly NoSQL involved here. Just to give you a quick view as to what DB4O looks like, typically DB4O is pointed at a file, so you're going to be limited to whatever the limitations on file size are for your particular platform. So 32-bit operating system, typically the maximum file size is like 4 gigs. 64-bit operating system, okay, now the file pointers are 64 bits wide. You can get up to ridiculous numbers again, assuming you have that much storage. Again, this is assuming a single file, so there is no partition tolerance here. As a matter of fact, DB4O has no way of doing partitioning on its own. Okay? But in terms of storing an object, right, again, person is just a straight up POJO, no annotations required, constructor, getter, setter, getter, setter, getter, setter for first name, last name, and age, bang, set, puts it into the database, commit, writes that transaction to disk, the end. No XML was introduced during the making of this example. Okay? No angle brackets were harmed during the execution of this fetch here. This is the prototype-based approach, which a lot of object APIs use. If you remember Hibernate way back in its early days, they had a similar kind of prototypical-based query where they said, give us the POJO, where the POJO has fields filled out with what you want the predicates to be. So for example, down here at the bottom, db.get, I'm newing up a person with the last name Neward set. This means select star from person where last name equals Neward, to translate it into SQL terms. The problem with the prototypical approach is A, you have to allow for nulls in each of your fields in order to be able to use it as a prototype. This creates a particular problem for things like primitive types. You'll notice I'm passing a 0 there. What if I actually want to find people in the database whose age is 0? DB4O can't tell the difference.
okay? And so this is where you would have to write the native query and so forth. But if you just want to do simple gets and stores, if you just want to take an object, store it off, pull it back, you don't want to do any complex query, the prototype-based API is straightforward, it's simple, you're off and running. The native query stuff will say db.query parens new predicate, angle bracket person, because it is Java 5 and it is genericized, and then you override the predicate method to say, okay, here's the object return o.getAge greater than 21. Meaning true, yes, include it, false, don't include it. Again, db4o analyzes that query, figures out that this is what you're trying to do. It doesn't have to actually execute your Java method. It does the bytecode analysis to do it in a more optimal way, which is really freaking cool. Updating an object, well, basically it's, Java 101. Once you've got the object, do a set and then just pass that same object into db.set and it's stored. Okay? Just like with Hibernate, you can only store the objects that you have fetched from the database if you want to do an update. Otherwise, it'll assume that it'll be an insert. So if we try to do the functional thing and I create a new person object with Matthew's age incremented, db4o will assume that's a different object and there will be 2 copies of Matthew in the object database. Which, quite frankly, he's a handful by himself. I don't want 2 of them. Okay? Mongo, document-oriented database. Mongo, in many respects, is one of these databases that looks and feels, aside from the shape of its data, it looks and feels and behaves much like a traditional server-based database does. So Mongo is expected to be sitting behind the firewall. It's expected to be sitting next to your app server. It's expecting to receive queries on the server side, et cetera, et cetera, et cetera. Okay? This is a little bit different from Couch, which we'll talk about next. It's a documented-oriented approach to data. It does support MapReduce. The query language that Mongo uses is JavaScript. As a matter of fact, this is a fairly common meme. If you're not seeing JavaScript as a legitimate programming language, you're really short-sighting yourself. Doug Crockford recently uttered the quote that JavaScript is Lisp for C hackers. In other words, if you ever wanted to experiment with Lisp, but you could never get past all of the irritating, silly parentheses, you know that's what Lisp stands for, right? Lots of irritating, silly parentheses, right? JavaScript is actually probably the closest thing we have to Lisp using curly brackets and semicolons. And actually, the semicolons are optional in JavaScript, so we'll just say curly brackets, okay? It's a very powerful dynamic language. Mongo embeds it in order to be able to do the query. So where a traditional relational database uses SQL, Mongo uses JavaScript, okay? Mongo's written in C++. The reason they did that, they said, was for performance. So generally speaking, Mongo is considered to have faster writes and faster reads than other relational systems. That's kind of a bogus claim because there's really nothing intrinsically faster about native code as opposed to managed code. Mongo doesn't have all of the ACID transactional guarantees around it. That's part of why it is faster than a traditional relational database. Because most of the other relational databases are written in native code as well. Okay? A Mongo server will hold any number of databases, where a database is made up of a number of collections, where a collection is made up of a number of documents, where a document is basically a JSON document. Technically what Mongo has done is they've taken JSON and extended it. They've added some additional capabilities, including the ability to store binary data, so they call it BSON. Binary script object notation. Okay, it doesn't really hold. Just call it BSON. All right? The data types down here below, you can see there, including object IDs, OIDs. Every document that gets dropped into Mongo gets an OID associated with it. So a Mongo document can, in fact, hold a reference to another document, but it will not automatically follow that reference for you. If you try to dereference that value, what you get back is this big, long, opaque hexadecimal value. You then have to go back to Mongo and ask it to fetch that OID for you as well. That's one of the key differences between Mongo and db4o. db4o will automatically pull back the dependent objects. Mongo says you have to go get them yourself.
That's what makes it a document-oriented database as opposed to an object-oriented one. Generally, when you're working with Mongo, you do a number of, connect to the server, authenticate, look at the database root, create a collection, get those elements in the collection, populate it, et cetera, et cetera, et cetera. Generally speaking, most people will tell you that Mongo is not transactional. That's not entirely true. Writing a single document to Mongo is transactional. It's writing several documents that may not be. And it can be if you so desire, but again, you take a performance hit when you do. Mongo supports querying. You pass a document as the query. So in other words, in order to execute a query against Mongo, you pass in a JSON document that has a field describing the query where the query is written in JavaScript. Okay? And you can find them either in a predicate clause or via code block. You can take JavaScript, store it on the server, and ask the server to execute it before it hands the data back to us. So in other words, Mongo supports JavaScript stored procs, which is kind of interesting. The operators that are available inside of the query language, and I think they may have introduced a few more as part of 2.0 that are not here, but you can see down below that little blurb of JavaScript there. That's actually what a query document is going to look like. Again, it's JSON, so we have a field, in this case called field, right? Whatever the field is, age, where we want to say it's greater than 1, less than 5, etc. Okay? It's a bit odd. Sir?
So, is there really any advantage to query language that is JavaScript or some other query language or Java as opposed to SQL being a perfectly valid query language? Is there anything about SQL itself that says it is unsuitable for use in a sharded or inconsistent, potentially inconsistent database?
You want the red pill or the blue pill? Bearing in mind, too, by the way, that there is a huge political minefield that you just walked into.
Yeah, exactly.
Right?
It says, is it a rejection of SQL for religious grounds or for technical grounds?
Okay, technically, what the NoSQL guys should have named themselves is no relational.
Exactly.
Right? If we allow, when we talk about SQL in this conversation, if we say not necessarily SQL 92 standard SQL, if we allow for a certain extension of the syntax, or if we implicitly take away certain things in the syntax, you're right. We could definitely do selects and wheres and so forth. The problem here is that if you have SQL-like syntax, people expect it to be SQL. And so then when they don't have their group bys and their order bys and their sum and their count and all their other aggregate operators and so forth, when they don't have the full range of SQL 92, they consider it to be broken. This is what happened with OQL. OQL looks very much like SQL. Select person P, or select P from person where P.age equals, etc. And so people started expecting SQL to be there, and it wasn't. It was OQL, and it just felt weird. Especially when you could actually make method calls in the middle of this query, which was perfectly legit, right? So in some respects, we want to put SQL aside, if for nothing else, just to make sure conceptually our heads are pointed in the right direction. Now, having said that, some of the NoSQL databases, and yes, Cassandra, I'm looking at you, have created like a JDBC driver, so that you can pass SQL into the driver and it will do the necessary twisting to turn it into a Cassandra style fetch, right? Using the Cassandra API, because Cassandra doesn't really have a query language. It just says, here's a bunch of columns, go, right? There is no query language for Cassandra. The Neo4j guys, they kinda sorta are, they kinda sorta had a pseudo type query language, but the general API is to use visitor path, because that's a graph database. And so if you were saying select no, select arc, select no, this just really doesn't fit anywhere inside the SQL lexical model. Could we take SQL and apply it to Mongo? Yes. Has anybody done it? No. Could we take SQL and apply it to Couch? Probably. Has anybody done it? No. Is it a worthwhile project? I think it would be a worthy experiment. And so next year's JAX, when you're done with that, you report back to us as to how successful it was. We cool? All right, awesome. All right, so moving on. Couch. Couch is another document-oriented database. Again, it stores JSON documents. The thing about Couch is it has no ad hoc query language. Everything done in Couch is done via REST, so it's all HTTP gets and puts. So if you do not have the HTTP 1.1 specification memorized and you start to use Couch, you will. There is no low-level driver for Couch. Everything is done via HTTP. And this is both limiting and liberating at the same time. Because one of the things we can do with Couch is we can actually have Couch store HTML. That HTML can be presented to the user directly because the way in which you find a document in Couch is by doing an HTTP GET to that particular document ID. And so what the browser does the GET, the browser gets back HTML, the browser displays it. That's what browsers do, right? And if that HTML in turn has some JavaScript, which does an HTTP put or an HTTP post back to Couch, well, what does Couch do with that? It stores the data. And then it can send back a document. In other words, Couch has the ability to turn into a one-tier app server, where it is app server and database both. There are many people in the Couch community who have said point blank, I have no idea why anybody would ever want to use anything other than Couch for doing any of their server-side web-based development because it's everything rolled into one schmuck. Now, I'm not necessarily advocating that position, but it is an interesting position. And it is one of the fascinating things about Couch is it will totally fuck your brain up. It will force you to completely rethink some of the core assumptions we make about building Java server-side applications, about building web applications. Now, again, do I want to put 50 petabytes into Couch? Not into a single Couch system, but definitely I can have a number of Couch instances, and Couch has some really interesting bidirectional replication. So again, if you're building a Couch app, where again, remember the code, the documents are stored in Couch, you put it into here, well, it replicates to this node, which replicates to this, so deploying the application into one of these nodes means eventually it goes all the way around the ring. You don't have to worry about, because again, the eventual consistency model kicks in, you don't have to worry about taking them all down simultaneously and bringing them all back up again, et cetera, et cetera. It's a very different way of thinking about how we build applications. Couch has no locks, it uses multi-version concurrency control instead. So in other words, it'll write versions of the documents down and tag it with the version number. What this means is technically Couch will keep a history up until you purge the database, at which point the history goes away. So don't treat it like a chronological database. You could put your own version numbers on it, but don't use Couch's if you want them to stick around. I mentioned this, curl, if you haven't used it, is a great tool for doing HTTP directly. It's a schemaless key value store. Again, everything is essentially JavaScript, which means that you want a new field, add it, the end. All of the views, all of the queries and so forth are done, like I said, via HTTP gets. Map reduce is a core part of this. You can define a view as a map reduce, which then says I want to find all of the documents that have a last name of something or other and so on and so forth. So we can do bulk inserts, blah, blah. This is all Couch stuff. You can look at this in the slides later. Cassandra. Cassandra is all about building large collections of data, servers, nodes running in a cluster. Cassandra has one of the strangest data models you will ever see. It has columns, which are a triplet of name, value, and timestamp. And then we have super columns, which are columns containing other columns. Oh, I'm sorry, column families contain other columns, and then super columns have columns that have subcolumns. What? This one is a bit weird. I have not fully grokked the Cassandra data model or where exactly it's useful, but the thing to realize is that on the surface of it, it looks kind of, sort of, pseudo-relational. It's not. It's really, really not. But Cassandra is about clusters of servers containing data that's spread around the ring. It looks at a row key in order to figure out which server it's going to write this to. When we start thinking about collective machines cooperatively storing tons of data, that's the space that Cassandra wants to live in. Okay? And finally, Neo4j, as I said, it's a graph-oriented database. Specifically, if you want to try to model something that's not specifically hierarchical or specifically relational, table column oriented, Neo is your boy. So again, if we're trying to model social relationships, if we're trying to model code history under a distributed version control system, stuff like that, Neo has a much better model for doing that than any of the other stuff that we've seen so far. So definitely worth looking into. I know Ian Robinson, Jim Weber did a session on Neo, I think it was yesterday. But Ian Robinson, Jim Weber, two thought workers who have gone over to Neo. Anytime a thought worker leaves the company and goes to somebody else, you want to keep an eye on that somebody else, because thought workers don't leave except for really exciting or they're tired of traveling. This is definitely one to keep an eye on. Supposedly, I've heard that SpringSource, VMware, is also very interested in these guys. We may see an acquisition at some point in the future. So definitely, this is one of those to keep an eye on. I waved my hands a lot during this talk. I just said, yeah, just assume that what I'm telling you is true. I could be lying. As a matter of fact, I did lie. Somewhere in this presentation, I lied to you. Your challenge is to figure out where. Bye-bye.